Hello, my name is Rudraksh Nair, and today I'll be presenting my research for proteolysis targeting chimera or PROTAC mediated degradation of MNK1, a novel therapeutic strategy for glioma treatment. So what are gliomas? Gliomas are a class of highly aggressive brain tumors that remain amongst the most treatment-resistant cancers due to their invasive nature, limited drug delivery across the blood-brain barrier, and frequent recurrence. Gliomas target glial cells, cells that support and protect neurons in the central nervous system. In the United States, approximately 15,000 people per year are diagnosed with glioma cancer. Symptoms include headaches, seizures, cognitive decline, motor weakness, and vision problems, but they vary in accordance to tumor location. Unfortunately, there is no cure, but there are potential treatments to help the patients. Glioma occurs in four grades of aggressiveness. The first grade, or grade 1, is the least aggressive. Grade 2 can grow and recur after tumor resection. Grade 3 is aggressive and fast growing. And finally, grade 4, also known as glioblastoma multiforme, is the most aggressive and has a poor prognosis. Current treatment strategies for glioma involve surgical resection, radiation therapy, and chemotherapy, with temozolomide being the primary chemotherapeutic agent for high-grade gliomas. Despite these interventions, treatment efficacy remains limited due to several challenges. The invasive nature of gliomas makes complete surgical removal difficult, and the blood-brain barrier restricts effective drug delivery. Additionally, gliomas often develop resistance to TMZ and radiation, and the immunosuppressive tumor microenvironment hinders the success of emerging immunotherapies. Consequently, tumor recurrence is nearly inevitable, particularly in GBM, leading to poor long-term survival rates. The MNK1 protein, or the MAP interacting kinase 1 protein, is a key regulator of mRNA translation, primarily activated by the MAPK or ERK pathway. Its primary function is to phosphorylate the eukaryotic initiation factor 4E, which plays a crucial role in cap-dependent translation, a process often hijacked by cancer cells to promote proliferation and survival. MNK1 is implicated in several cancers, including glioblastoma, breast cancer, and leukemia, where its overexpression correlates with tumor aggressiveness, therapy resistance, and poor prognosis. In gliomas, MNK1 contributes to tumor progression and survival by enhancing the translation of oncogenic proteins, making it a potential therapeutic target. Recent findings suggest that MNK1 inhibitors could improve treatment outcomes by disrupting cancer cell proliferation and overcoming therapy resistance. Recent advances in targeted protein degradation have led to the development of proteolysis targeting chimeras, or PROTACs for short, a novel therapeutic drug strategy designed to fully break down disease associated proteins rather than only inhibiting their activity. PROTACs are heterobifunctional molecules composed of a ligand that binds the target protein, a ligand that recruits an E3 ubiquitin ligase, which marks the protein with a chain of ubiquitin, and a linker, thereby promoting ubiquitination and proteasomal degradation of the protein. This technology offers significant advantages over traditional small molecule inhibitors, particularly in targeting proteins that show resistance to modern treatments, such as transcription factors and scaffolding proteins. Several PROTACs have demonstrated potent anti-tumor activity in preclinical models. By leveraging the endogenous protein degradation machinery inside the cell, proteins can, PROTACs can represent a shift in drug development, with the potential to overcome disease-causing proteins and the resistance mechanisms to improve therapeutic outcomes in cancer patients. Investigating the potential of PROTACs to target oncogenic proteins such as MNK1 may open new areas for the treatment of aggressive and drug resistance cancers. As seen in the figure in the presentation, you can see how the PROTAC acts inside the tumor microenvironment, in this case, in the glial tumor. For the methodology, we used UniProt to find the amino acid sequences of MNK1 and CRBN, or the cereblon protein. This provided functional annotations and sequence information necessary for structural modeling. The three-dimensional structures of both proteins were predicted using AlphaFold 3, and their topologies were further validated with Proter to highlight functional domains and membrane localization features. To confirm biological relevance, the Human Protein Atlas was used to evaluate the expression of MNK1 and CRBN in glioma and other tissues. Potential ligand binding pockets on both proteins were identified with P2 rank, which guided the docking regions for subsequent simulations. Docking studies were conducted using the HDoc server to model interactions between MNK1, CRBN, and a library of 10 designed PROTACs, P1 through P10. These heterobifunctional molecules contain variable linkers to optimize ternary complex formation. For each candidate, docking scores and poses were analyzed to determine whether the PROTAC could simultaneously engage MNK1 and CRBN. The docking complexes were further evaluated using PLIP to identify stabilizing interactions such as hydrogen bonds, hydrophobic contacts, salt bridges, and pi-pi stacking. Binding free energies were calculated with Prodigy Lig to quantify the strength of interactions. Additionally, all PROTAC candidates were converted into small strings with open babel and assessed for drug likeness and pharmacokinetics using ADMET AI, focusing on solubility, intestinal absorption, hepatotoxicity, cardiotoxicity, and blood-brain barrier penetration. Visualization of docked complexes and degradation mechanisms was performed with Chimera X and BioRender. Here are the predicted binding sites that we found using HDoc, and we modeled them in Chimera X. And here are the molecular docking interactions, which show the interactions between the amino acids in the protein and the PROTAC. The structures of MNK1 and CRBN predicted by AlphaFold 3 displayed well-defined functional domains consistent with their biological roles. Topology validation through Proter confirmed correct structural organization, while expression analysis using the Human Protein Atlas verified significant levels of both MNK1 and CRBN in glioma tissues, supporting their selection as a target ligase pair for PROTAC design. Binding pocket prediction with P2 rank identified multiple high confidence regions on MNK1 and CRBN suitable for PROTAC binding. These pockets were used to guide docking simulations. Among the 10 designed PROTACs P1 through P10, P4 emerged as the most promising candidate, demonstrating the most negative binding energy. Conversely, candidates P6 through P10 showed weaker interactions or misaligned conformations, making them less suitable for further development. Pharmacokinetic and toxicity profiling of all PROTAC candidates using ADMET AI demonstrated favorable properties across the library. Importantly, radar plots and 2D structures generated for each PROTAC further illustrated the balanced drug likeness and bioavailability of the designs. The binding energy calculations obtained through Prodigy were also summarized in comparative plots. Taken together, these findings indicate that P4 represents the most effective candidate for targeting MNK1 degradation. Its strong binding affinity, structural stability, and favorable pharmacological profile suggest that it could serve as a promising therapeutic strategy for glioma and warrant further experimental validation. Our results identified P4 as the most promising PROTAC candidate, supported by strong binding affinity, stable ternary complex formation with MNK1 and CRBN, and favorable ADMET properties. The study provides a proof of concept for targeting MNK1 in gliomas using PROTAC-mediated protein degradation. Through structural modeling, docking, interaction profiling, and pharmacokinetic prediction, we identified P4 as a lead PROTAC candidate with strong binding affinity, stable ternary complex formation, and favorable ADMET properties, but lower blood-brain barrier penetration. These findings suggest that PROTACs could overcome the challenges of traditional inhibitors by inducing selective degradation of MNK1, thereby disrupting oncogenic translation and potentially enhancing therapeutic outcomes in glioma patients. Future work should focus on validating these computational predictions through environmental degradation assays, functional studies in glioma cell lines, and preclinical testing in animal models. If confirmed, PROTAC-mediated MNK1 degradation could represent a transformative therapeutic avenue for combating gliomas and improving patient survival. Nevertheless, the study has important limitations. Computational modeling cannot fully replicate the complexity of intracellular environments, including protein dynamics, off-target interactions, and proteasomal efficiency. Additionally, predicted pharmacokinetics must be validated in vitro and in vivo to confirm drug-like properties and therapeutic efficacy. Experimental validation using cell-based degradation assays and animal glioma models will be necessary to confirm the degradative efficacy, the degradative efficiency and safety of P4. Thank you.